everybody, and welcome to Traversing Arrow with Compressor Maps. My name is Liam Young. I'm a business applications engineer here with AFT. And today I want to showcase to you one of the brand new features in Arrow 10, the compressor map. In this webinar, I wanted to kind of set up a real life example, or just kind of like an example to get the feel of how you would actually take a real compressor map, get it into the software, what all the considerations are when you're going through that process. And to do that, we would first want to talk about kind of what our problem statement is for this live example, talk a little bit more about how you read a compressor map, what a compressor map is, those sorts of design considerations, how you actually transfer the data from the compressor map into the software, doing a little bit of a utility showcase, how it does its calculations, talking a little bit about some alterations you can do or things you can play with in the model to make it work well, as well as talk about some of the future development that we look to do with this feature. And we'll kind of close it all out with a nice key takeaway where at that point, be able to let you guys go. So hopping right in, we start out with our problem statement. This sort of live example starts out with us wanting to build a natural gas power plant. And the plant needs this delivery pressure, about 1,200 psig, to have its turbines operate properly. We have a natural gas line that we're looking to tap into to supply to this power plant after it's constructed. And some sampling was done at the tap point that we're looking to hook up to. And they found that the minimum pressure at that location would be about 400 psig, max pressure about 600 psi. And there's about 20 miles worth of pipe between the tap location and where they're looking to build the plant. It seems that they want to use a 36-inch line size to supply to the power plant, and they want it out of ANSI steel. So with the design considerations in mind, I went and developed a little bit of a sizing model. Wanted to use AFT Arrow for this because of its nice assumptions that go with this model. We're dealing with natural gas, so we're into compressible flow. We're looking for steady state operation once the power plant is up and running. We're okay with the one-dimensional flow assumptions. Pipes are going to be fluid full, and natural gas, so superheated. What we end up with is kind of this model on the right. We have that mainline tap point where we'll kind of have those 400 and 600 psi requirements, about 20 miles worth of pipe with our compressor station along that line, delivering to this power plant, which will be our 1,200 psi delivery pressure. Looking at the model, we can see here that I've built out just a couple of sizing scenarios. So in this first one, we have the min tap pressure, where we set up this assigned pressure to use methane as our natural gas. It'll help with run times later on. You could do a more complicated gas mixture, but to keep it quick for the analysis, we wanted to make that a little bit simpler. So 400 psi at 70 degrees. We're going to have that go down about 5 miles of pipe to our compressor station site, where we want to size it for about 12 mm FCFH, and then have that deliver back to the power plant at about 1,200 psig. The max tap pressure is almost identical, with the only change being that this inlet pressure is going to be about 600 psig. And so if we were, when we run these examples, we can see in our compressor fan summary that we have a compression ratio in the max pressure ratio case, about 2 at that 12 mm FCFH. And in the min scenario, we have a compression ratio of about 3 at that 12 flow rate. So we want to take this data over to some sort of manufacturer and have them kind of recommend a curve to us, And then we want to pull that curve back into our software in order to verify what operating points, RPMs, and things like that we're going to be working with. So we sent off that sizing data, and what we're expecting to get back from the manufacturer is a compressor map. But what is a compressor map? Generally, a compressor map is just a good guide of the different operating cases that you could use for your compressor. So the different lines are usually for different operating speeds. As you increase the RPM of your motor, you will be able to increase both the flow and head. And this operation is usually bounded by two different lines, which is a surge line and a choking line, where operating outside of those ranges is just not favorable for the compressor. So we put them as limits, and you really just want to be operating on one of these curves in this line. In addition to the operating lines, the things to consider are efficiency islands. Oftentimes they'll be written out as percentages like these, and they'll kind of have dotted lines showing the areas of operation on that curve where those efficiencies would be. And then another important thing is a lot of compressor maps try to be normalized or non-dimensionalized in order to be more applicable. Compressors maps are, well, compressors are very dependent on their inlet conditions for operation. So what these normalized or non-dimensionalized units attempt to do is allow manufacturers to give out curves that can be used for fluids other than what the testing fluid was at different operating conditions. So in this case, the RPMs in a compressor map normally can be found in the sort of non-dimensionalized form, as well as the flow can be in a non-dimensionalized form. So what is that normalized value? They're usually given by these relationships, where to normalize the flow, you're multiplying the testing flow rate by the square root of the stagnation temperature at the inlet over the pressure, stagnation pressure at the inlet. So this is just attempting, even though it says it's non-dimensional, it is a very dimensional set of units. But really what it's trying to say is it's trying to make a term that's independent of those inlet conditions so that it is easier to pull into different scenarios. You could also just correct the mass flow for the inlet conditions. So you could take your reference conditions and then test it against your actual conditions and correct that flow. These are the two different mass flow rate options that the software currently accepts. So whenever you're dealing with compressor map, you're always going to want it to get into one of these forms. You also will want to non-dimensionalize the speed. Again, you're just kind of correcting this omega, which is going to be an RPM, using the square root of the temperature to get that speed independent of the temperature of the fluid. The other important things to note are this compression ratio. It's always going to be the stagnation pressure ratio. So the outlet over the inlet conditions, just for that way it's always dependent on the current conditions of the fluid that you're working with. And then the compressor efficiency zones, like I said before, they're usually like dotted circles, regions on these compressor maps. And they shouldn't be confused with polytropic efficiency. They are isentropic efficiency zones. So be sure to be careful with that. But with that, let's hop into the model file and actually talk a little bit more about how we're going to implement our compressor map into this model file. So what we're going to want to do is clone this scenario. We want to maintain those min and max conditions, but we also want to, instead of having the sizing scenario, we want to do it with a compressor map. Now that we kind of have this scenario built out in our model file and ready to accept data, let's go take a peek at what our compressor curve actually looks like. So we sent out that sizing data and ended up getting a compressor map back, and it looked something like this. There's a lot of important information on this map that we're going to try to carry over into the model file. And so we can see in our compressor map, we have pressure ratio on the left, which is good. That is what we saw earlier, how the software accepts the pressure side of this. If we come down here and we look at the flow rate, we'll actually notice that we have standard flow over pressure, which is a little bit different than the corrected units that we were expecting. When we were looking at the non-dimensional units, the equation for that's actually equal to the mass flow times square root of temperature over pressure. So we would expect a square root of temperature units with this. So we're going to actually have to make that correction ourselves as we move forward. We'll also notice that all of our speeds are in RPM. We want that to be in terms of non-corrected speed. So we're also going to have to make an adjustment there during this curve. When I work with a compressor map like this, I like to use usually a web plot digitizer tool to grab all of the data off the curve as accurately as possible. And so with this curve, I did that and pulled it into an Excel document. So we can see at each of the RPMs, I pulled data from those curves, and we just have a range of different points from each of those operating conditions. What we want to do with this data is make sure that we're correcting it towards the terms the software accepts. So in that case, we want to first off non-dimensionalize the speeds. So I just took those, and we have 5,000 to 10,000 RPM. The specific inlet temperature for this compressor was tested in was 70 degrees Fahrenheit, which converts to 529.67 degrees Rankine. You always want to put it into absolute temperatures. So if you're using the metric units, Kelvin, or the English units, the Rankine scale. And so if you take 5,000 divided by the square root of this, we can remember from the slides that omega non-dimensional is just equal to omega over the square root of the inlet temperature. In terms of degrees Rankine. So with that, you can just do that really quick here, and we'll end up with these values in column C. Very similarly, we have to non-dimensionalize the mass flow. If you remember right from our compressor map, down here at the bottom, we're flow over pressure when we want flow square root of temperature over pressure. So we can do that, a very similar correction with the mass flows here to kind of get our data set that we're going to be inputting into the curve. After this, we can go into the compressor form. Since we're inputting a compressor map, we just want to hit this compressor map button and begin entering curve data. So very complicated form with a lot going on, but we're going to try to just step through all of the components of it. First off, we have our table where we're entering data for a single curve. And there's a variety of different units that you can do. Talked a little bit earlier about how there's mass non-dimensional or mass corrected that you can use here. Even though we say non-dimensional, it is still a very dimensional unit. So you're going to want to specify the exact units that your compressor curve is going to follow. In my case, that's FCFD. Stagnation pressure is the only, in terms of a ratio, is the only option for the y-axis currently, but it could either be in a decimal or a percent. Go back and check our curve real quick. We'll notice we're in a decimal, so we'll want to keep that there. And then efficiency. You'll notice I have efficiency data in here written as percentages. If we check this curve, it was actually given in horsepowers per PSI. I ended up using a similar curve to pull efficiency data off of. So the results might not line up exactly with these horsepowers, but they should be pretty close. So with that, we also have different curve fitting types, depending on how many data points you have. Interpolated can give you nice curves. We also allow for the polynomial. In this case, I'll be using interpolated just because I have a large number of data points from my curve. And then the next important thing is we want to make sure these pressure conditions are met. The conditions for the curve I was using had a 500 psig inlet temperature or inlet pressure and a 529.7 degrees Rankine stagnation temperature. So want to make sure that those are inputted and correct. And then from there, we can start making our first curve. So as we're going to be inputting these curves, we're going to enter data for a single curve at a time. And we're going to start building that compressor map. So we're going to start by building our first curve. And then we'll start grabbing the next, and we'll keep building them up kind of like this. And what the software is going to end up doing at the end is using these curves to actually interpolate between them. So it could find a point here in terms of flow, and it'll just kind of interpolate between the two on a new curve based on the RPMs you've inputted to get this new, so you'll get a new curve for different operating conditions. So I'm going to start by grabbing our first non-dimensional speed, which is this 217. We'll just take that really quick. And we come over into this form on the right. So this is where we're going to end up with our list of different operating speeds, where we'll enter all of the curve data for each of them. In this case, we have this unspecified speed, which is going to be our first one at 217, which corresponds to our 5,000 RPM curve. So we can grab that data. And we can paste that in here. We can then hit graph data to have it create the curves. And then we can update configuration. When we go into clicking on this, we can see that we'll have a composite graph with both the stagnation pressure ratios and the efficiency charts build out. And then we can go and start to create our next curve. So what you just do is you create. This will create a new line item below this one. And we go back in to grab our next non-dimensional speed. So we take this 260, paste it in here. And then we want to go grab the data for the 6,000 RPM curve. So we'll grab that real quick and paste that in here. Graph that data, update configuration, and then we'll see we now have our 260 RPM curve. One more time with that, it's grab this 304, hit create, paste in the 304. 304 corresponds to the 7,000 RPM. So we'll grab that curve data. And then paste it in here. Graph that data, update the configuration, and we're on to that third one. I'm just going to continue to repeat this process for the last couple of curves and just talk a little bit more as I do. So grabbing, basically as we're grabbing these curves, we'll continue to expand the operating conditions that the compressor map can handle. So in this case, I'm actually leaving out the highest and the lowest RPMs that the compressor can operate at. Only reason was just to save time. You could definitely add them in, but I know that my compressor is not going to be operating in those regions. So I just wanted to leave those out so that I'm not adding an extra 2 curves during this process. But it does end up being pretty quick once you kind of have an Excel spreadsheet set up like this. It's not too tedious just to go through and add another item to each curve. And here we are finishing up with the last set of data. So with that, I can hit OK. And then OK to save all that data. So going back in, we can see that we now have different curves in this configuration. This is mostly just for viewing the curves here. And at any point in time, you can type in a rated speed, and that will be the speed at which it's treating your compressor like it's operating at, and we'll try to find a curve, generate a curve at that speed to use for your analysis. Here, I want to make sure I'm using determined from efficiency data for my actual scenarios. So coming in here, we're just going to want to copy data from parent junction. With this, we get all of that data in to that compressor, and we'll want to do that again for the max tap pressure. Copy from parent. So next thing I wanted to kind of go over was something that I ran into when I was first building out my model, which was compressor maps tend to have a lot of operating conditions that can satisfy a system, which can make it mathematically challenging to find a solution that works, the exact solution that works for your system. So when I was building out my model, if I were to basically run these scenarios as is, I would find that this min tap pressure would give me a convergence error, and this max tap pressure would give me a solution that was incorrect for the system I was designing for. So I kind of wanted to talk a little bit about that. From our sizing scenarios, we know that the compressor map is going to want to try to find a compression ratio of either 2 or 3. I'll talk about the 2 right now. So it's going to try to find some sort of solution kind of on this line. And the only thing that's actually bounding it is the curve that we're going to specify RPMs for. So we might try to specify something like this. And what we want it to find is this point here, where those two are lining up. But during its solution progress, it has to make guesses along this line in order to find that point. And what can end up happening is it could start out a flow guess that's really low, and you end up somewhere in this surge area where your curve is doing some wonky thing as it's extrapolated out. And this can throw off results, send it down weird paths, give it weirdly high compression ratios for flows that don't make sense. And that's where you get those convergence errors. Or it could send the software running off into a direction that just doesn't make sense. So what I found is it's really good to give a little bit of help to the software. Give it just kind of a nudge in the right direction. And you can do this by changing initial guesses. So in my system, my flow is in the millions of standard cubic feet per hour. From our sizing scenarios, we know it's about roughly 12 that we're looking for. Whereas the standard initial guesses in the software are much, much lower than that. So giving it a nudge in this right direction is kind of how we get around those. It'll start the solver guessing in areas more towards where that intersection point I showed from earlier is. So highly recommend. In my case, I'm doing these all manually because I only have about 4 pipes, but you could also just give it some initial guesses through like a global edit. That would work well too. And you don't really need to know, where everything is. It's just getting it roughly in the ballpark. I'm pretty sure if I put like 1 standard cubic feet, so order of magnitude, that's where you'd want to make these guesses. So once we add those, we can give this model a run. I forgot to put in my rated speed. So talking a little bit more about how we should do rated speeds. For this, I'm going to try to update these to give a nice, make sure they're all have the same x-axis so that we can view them more easily. But we want to make sure we're selecting an RPM that makes sense for the curve at the operating conditions we want. So in this case, we can take a look at our what compression ratio we're expecting. So this is the max flow case where if you remember from our sizing scenario, we want a compression ratio of about 2. So if we take a look at our 8,000 RPM case, we can see we have a nice compression ratio of about 2, but it sits intersecting it's intersecting somewhere around 11, and I think we wanted it closer to 12. So we can put in just a little bit higher of an RPM, maybe let's say 8,100, try to get that as close to there as possible. And with that, this scenario should be good. And if we go into the min scenario, again, we're wanting to give this its non-dimensional speeds. Again, we'll just run through real quick. Give this 20, 20. Looking good. So in this case, we're in that min flow. We want a compression ratio of about 3. So if we take a look at our 10,000 RPM curve, we're looking at compression ratio. Looks like going to intersect somewhere around 14 or so, 15, somewhere in there. So we probably want to drop this down from the 10,000 slightly. Let's call it drop by 100. And so now the software, like I was saying earlier, is going to basically, it understands the curves look something like this. So in this like 9,000 RPM case, it's going to basically, it knows this curve, it knows this curve, and it knows it wants a compression ratio of about 3. So an interpolation is just going to occur kind of along a 9,000 RPM curve in here. And wherever it intersects that curve is kind of where it's going to operate at. So maybe somewhere around 10, I believe would be my expectation here. So give it a nice run. Can check here, and we can see we get that nice compression ratio of 3, around 11 mmFCFH. And in the max case, run that real quick. You can check compressor fan summary, see it found a compression ratio about 2 with a mass flow about 13. So looking at this, what we set out to do was size a compressor for this compressor station that it could meet those 1,200 pressure demands while giving a large amount of mass flow. And it does seem like this curve is giving results that would be good for this system. Another good thing to note with this is these operating conditions that we're running at tend to be towards the middle of the curve. So operators, when they're actually using the system, will have some leeway to push RPMs up in higher demands and push things down in lower demands. So there does seem to be a good bit of leeway with this curve for various operating conditions. So it seems like it could be a pretty good recommendation. So with that, we've talked a little bit about what compressor curves are, what are some of the considerations you need for the units when you're actually implementing them into the software. And we were able to check the results and see that our compressor station is sized well. So with that, we can actually move on to some of the features of the compressor map feature. So compressor map is kind of a new feature in Arrow 10. There's a lot of different things we're wanting to add and update to it. One of those is allowing users to enter inlet guide vane angles. Inlet guide vanes change operation a lot in compressor curves, and we would love to have people be able to adjust their curves to fit those. Guide vanes can do a lot of different things. Sometimes they're numerically controlled to help the compressor out. So we're really looking to try to implement just a way for people to add enter angles of those vanes in so that we can adjust the curves for steady state operation. We also want to expand the visual representation of the compressor map. As you saw when I was going through the compressor map properties window, I had to adjust the axis, and even then I couldn't overlay all of those curves on top of each other. So that's a little bit of utility we're looking to add, basically give people the ability to see the compressor map as its entirety. We're also thinking about maybe making the option to have a compressor map versus system curve, just so you can have a more visual representation of different operating conditions that you could be working under. We also want to allow the user to specify reference fluid. Currently, we just assume that the testing conditions for your fluid are the reference fluid you're using, which worked well for the curve that I was using because it was tested in natural gas. But oftentimes those curves are tested in air or other conditions. And so giving the users the ability to specify what that reference fluid is, so corrections can be applied appropriately. We're also looking for feedback on this feature at any point in time, whether there's new units you want to add, new utility. We just always want to hear back from you guys. Feedback on this feature is absolutely welcomed. If you have different compressor curves that aren't mapping well or considerations we didn't take into account, please let us know. With that, we're approaching the end quickly. Key takeaways though are Arrow can now receive an entire compressor map, which can now help you with all of your different design considerations. When implementing these, be sure to check units carefully. As we saw, they're not always mapping cleanly. Sometimes you might have to do a little bit of conversion on non-dimensional speed or readjusting some of those flows. Compressor maps tend to be a lot of work up front. You have to specify a whole bunch of different curves, but it saves time in systems where you're looking and trying to check different operating RPMs. I know I've done work where I probably had 10, 15 different RPM operating cases for a system. And during those times, I would have to, back and forth, grab a curve, test it, say it's not right, and then do that again. So compressor map makes those iterative processes obsolete. The more detailed, the better. Compressor maps can have multiple solutions inside of the map. So make sure it's finding the right one by giving it as good of information as possible. And this is a brand new feature. So if you can, give us feedback. We want to hear about it. We want to improve it. It's meant for you guys. So let us know. For any extra resources, we have a plethora of other webinars, recordings, blogs, documentation cycles. Reach out to support if you have questions, or just call us. We also do a little bit of consulting. So if there's any complex engineering questions that you're wanting to have a flow expert's opinion on, let us know. Thank you everybody for attending, and I hope you all have a wonderful day.